Zeal Education Society, redefining excellence.
Good morning to everyone. Myself, Dr. Mahadev Unde, Professor in Electrical Engineering Department, Zeal College of Engineering and Research, Pune. In a previous video lecture, we have learned the Potier method of finding the voltage regulation of alternator. Now, in the Potier method is based on separation of voltage drop due to the leakage reactance and voltage drop due to the armature reaction. And it has been also studied that the voltage regulation obtained by Potier method is superior or more accurate as compared to the voltage regulation obtained by the EMF method and the MMF method. Now in this today's video lecture, we are going to solve a numerical based on it. Okay, now let us start. I have taken the numerical which has been asked by the SPPU in November 2012. I will read the question. Okay, so now 10 kVA, 440 volt, 50 Hz, star connected alternator has open circuit characteristics as given below. The feed current and then the open circuit voltages line to line value, and the same is converted into per phase by dividing it by √3 because alternator is star connected. Okay. Now it is further observed that the feed current of 4 ampere is required to circulate short circuit current equal to full load current. That means we can obtain the point A from this information, that is the x coordinate of point A is the 4, 0, and for 0 power factor full load curve, that is the 14 ampere excitation is required. 14 ampere excitation is required. 14 ampere excitation is required to generate 500 volt line to line value. Assume that the armature resistance is 0, that is neglected. Determine the voltage regulation at full load and power factor 0.8 lagging and the 0.8 leading or a unity power factor also. Okay. Now we will check it. Now the per phase values, see the per phase values of open circuit voltages has been obtained and tabulated in the last rows. Okay. Now here it is. The step 1. The step 1 is plot the OCC and 0 power factor full load curve where the point A for a full load 0 power factor is 4, 0 and the coordinate of point B are 14, 288.675, where 288.675 has been obtained. That is here it is, the 14 ampere excitation is required to generate the 500 volt, 500 divided by √3, that is equal to 288.675. Then draw the 0 power factor full load curve also as shown here. Now pay attention here. Now here the every data is taken over here also, the open circuit characteristics and 0 power factor characteristics. The short circuit test, IF equal to 4 ampere, that is IF equal to ISC equal to 4 ampere, it is given. The field current required is 4 ampere and 0 power factor full load curve. The 14 ampere excitation is required to generate 500 volt line to line, that is equal to 288.675. Now take the proper scale, x-axis, there is a field current and field current 1 centimeter equal to 1 ampere is considered. And for the y-axis, the 1 centimeter equal to 25 volt is considered. Okay, so now pay attention. So 1 mm equal to 2.5 volt. Okay, so let us plot the OCC, and the OCC is as shown. OCC has been drawn as shown in this. See, this is the OCC. Okay, now correspond to OCC. See, the OCC initially the OCC is a straight line, and later on because of magnetic saturation it becomes a curve. Now say draw the tangent line, that is OL shown by the dotted, tangent to the OCC. Okay, then how to locate the 0 power factor curve? 0 power factor curve, we have to locate the point A. Now for the point A, the coordinates are 4, 0. That means the field current required is 4 ampere to circulate the full load current equal to short circuit current. Okay. And the voltage generated is 0. Now point B is nothing but the excitation, that is the feed current required to generate the open circuit voltage equal to 500 in this case, and the 500 that can be converted into the phase value, and therefore 14, 288.675. So in this way we have obtained the 2 points. Now draw the zero power factor full load curve just parallel to the OCC. Okay. Now pay attention, OA is nothing but the feed current required to circulate full load current equal to short circuit current, and that is measured to be a 4 centimeter. It is 4 centimeter. So draw the BH from point B, draw the BH equal to 4 centimeter parallel to the x-axis, From point H, draw line HD parallel to the tangent line OL. Okay. Then from point D join B. So in this way we have obtained the Potier triangle BHD. Okay. Then draw the line DE perpendicular to the BH. Now D is parallel to the y-axis, and y-axis, that is the vertical component. Y-axis is the voltage. So what is the scale? 1 centimeter equal to 25 volt, and therefore D measures 26 mm, and therefore 1 mm equal to 2.5 volt. So 26 into 2.5, that is D equal to 65 volt, and that measures the voltage drop due to the leakage reactance, that is IA into XL. So D measures the voltage drop due to the leakage reactance. Okay. And now similarly measure BE. And what is BE? BE is nothing but the IF2, that is the feed current required to overcome the armature reaction effect, or to overcome the voltage drop due to the armature reaction, that is IAXA. So IF2 equal to 27 mm, and that is equal to 2.7 ampere. So IF2 is 2.7 ampere we have obtained. So what is B? B is nothing but the feed current required to overcome the voltage drop due to the armature reaction, and EH represent the feed current required to overcome or to compensate the voltage drop due to the leakage reactance, that is IAXL. Okay. So, and this triangle can be drawn anywhere, up to the OA. Okay. So in this way we have obtained the Potier triangle, we have obtained the voltage drop due to the leakage reactance, and we have obtained the IF2. Now from this leakage drop we have to obtain the voltage E. See, in this way. So VPH is 440 divided by root 3 equal to 254.03. Now step 2 is to find the voltage E at a power factor 0.8 lagging. So E is nothing but square root of VPH cos phi plus IRA bracket square plus VPH sin phi plus minus, you can use here minus sign also, plus minus IAXL bracket square, not XS. Here it is IAXL. Already we have obtained this drop. Okay. So in this way we have obtained that the answer is 297.6 volt, and it is very close to 300 volt because it is a graphical method. You have to just check it. Okay. So I will rub out this one, and here negative sign, here the negative sign can be used for a leading power factor. Okay. Now step 1, correspond to this 297 volt, how much feed current is required? IF1 is the feed current required to generate open circuit voltage equal to E, capital E, and that is equal to 297.6 volt. Okay. From OCC we can obtain the feed current IF1. Okay. Let us observe the graph. See, IF1 is 6.85, and the here see correspond to 297 volt, it is very close to 300 volt, just 1 or 2 mm line, 2 mm below this or 2 mm below this. Observe this one. Here it is 297 and 297 to here IF1 is 6.85. You can observe easily, quite easily, here it is 6, then here it is 7, here it is 8, and therefore it is very close to 7. So it is 6.9, close to 6.9. Okay, so the IF1 is 6.85 and IF2 is 2.7 ampere. So we have obtained IF1 and IF2. The next step is to find the resultant of these field currents IF1 and IF2. Okay, so let us find the resultant of this IF1 and IF2. See the step 4, to find the resultant field current IF for lagging power factor 0.8, the cos phi is 0.8 and therefore phi equal to 36.87. So draw the phasor diagram as shown. See here it is. See the OA is IF1 drawn horizontal or a reference. Then from point A draw the dotted line, vertical dotted line. We have to follow the same procedure that is used in MMF method. Then AB is nothing but IF2, that is 2.7 ampere, and draw this AB lagging the vertical line by an angle phi equal to 36.87. Now join OB is the resultant field current. OB is the resultant field current, and the angle between IF1 and IF2 is 90 plus phi, and that is equal to 126.87. So find out the IF equal to resultant field current equal to IF1 square plus IF2 square minus twice IF1 IF2 into cosine of angle between them, and it has been observed that the resultant field current is 8.74 ampere. We can consider it as a 8.75 for a graphical method. Okay. Now correspond to this field current, resultant field current, follow the same procedure that we have used in MMF method. So correspond to this field current, IF equal to 8.75 ampere. How much is the corresponding no load EMF generated? That is EPH. Okay, and it has been observed that it is 321.5 volt. Okay, let us check by the graph. So 8.75 and here it is. See 8.74 is here. Okay, correspond to this, the field current is close to 325. Here it is 300, here it is 325, and here it is 350. So it is close to 325, and it has been observed that it is 321.5. Okay, so here it is. Correspond to this, we can find out the voltage regulation. Voltage regulation is no load voltage per phase minus full load voltage per phase divided by full load voltage per phase. In other words, EPH minus VPH upon VPH into 100, and it has been, the answer is 26.57%. So this is the voltage regulation obtained at a lagging power factor. Similarly, we have to find out for the leading power factor. Okay. Now let us observe here. See, at a leading power factor of 0.8, the Potier method. Now already we have obtained that the voltage drop due to the leakage reactance is 65 volt and IF2 is 2.7 ampere. Now find out the capital E, that is VPH cos phi, VPH into cos phi plus IARA, but IARA is 0, bracket square, plus VPH sin phi minus IAXL. Earlier during the lagging power factor it was plus IAXL plus 65. So the answer E equal to 221.23 volt. Now find IF1. IF1 correspond to E equal to 221.23 from the OCC, and it has been observed that it is 4.3 ampere. Now we will check it from the graph. Now 221 point, where it is 4 point, just minute, 221 is close to 225, and it would be the feed current on this will be somewhere here, that is 4 point, the point is marked here. This is 4.4 or 4.3, okay, 4.3 or 4.4, okay, let us check it. It is 4.3 ampere from OCC, and IF2 is already obtained 2.7. Now similar to the previous method, that is MMF method, now I will not explain this thing. Directly let us find out the resultant feed current. So the resultant feed current is square root of, or okay, so how to draw this one, I will repeat it once again. Draw the OA, IF1 as a horizontal, then from point A, draw the vertical line, dotted vertical line, then draw the AB equal to IF2, leading the vertical line by an angle phi, then join OB, OB is nothing but the resultant feed current, and the angle between IF1 and IF2 is 90 minus phi, so 90 minus phi is nothing but 53.13 degree. Therefore, find out if the two sides of the triangles are known to you, you can find out the third side, and that for resultant is square root of IF1 square plus IF2 square minus twice IF1 IF2 into cosine of angle between IF1 and IF2, and therefore it has been observed that the resultant field current is 3.44 ampere. Now correspond to this 3.44, find the E0 or EPH correspond to this one, and it has been observed that the 3.44, the E0 is 190. We will check it on the graph. From the graph, 3.44. Here it is, just a minute, here it is 3, and 3.44 is somewhat close to this one. Now see, here it is 150, here it is 175, and then here 200. So it is around 190. It is around 190. Okay, so it is around 190. So let us check it. So it is a 190 volt, and therefore find the voltage regulation as usual, EPH minus VPH upon VPH, and answer is minus 25.20%. Minus 25.20%. This is the voltage regulation obtained at a leading power factor. Similarly, you can find out the voltage regulation at a unity power factor. Unity power factor cos phi is 1, phi equal to 0, sin phi equal to 0. And similar to this one, see, IF1, IF2, find out use the Pythagoras theorem and find out the answer is, resultant field current is 6.037. Let us assume 6 only, 6 ampere, because it is a graphical method. From OCC, find out the no load voltage generated from this one. Okay, no load voltage generated from this. So correspond to this one. Okay, before that we have to find out IF1 also. So IF1, see, E, we have to obtain E. IF2 is known to us, 2.7 ampere, and for the unity power factor, the E equal to VPH square plus IXL square. Take the square root of this. This is 267.21, and correspond to this voltage E. Find out IF1. Find out IF1 correspond to the generated voltage 262.27. From OCC, it has been observed that IF1 equal to 5.4 ampere. Let us check it. 260. See, here it is a 250. Here it is 275. Here it is 300, and 262 will be somewhere here. Pay attention. It will be around 5.4 or 5.5. It will be around 5.4 to 5.5. 5. Okay. So it is a 5.4. So in this way we have obtained the IF1 and IF2. So okay, IF2 is 2.7 ampere and IF1 is 5.4 ampere. Find the resultant of this, and it has been observed that the resultant current is 6.037. Okay, as a graphical method we can consider 6 only. Okay, so correspond to 6 feed current equal to 6 ampere. Find out the no load voltage generated from the OCC, and it has been observed that the corresponding voltage E0 is 275 volt. Okay, now let us check it from the graph. The voltage correspond to 6 ampere. The feed current is 6 ampere and correspond to 6 ampere. How much is the open circuit voltage? Open circuit voltage is, see here, it is 250. Just a minute. Here it is 250, here it is 275, and here it is 300. So when the field current is 6 ampere, the open circuit generated EMF, that is no load voltage, is 275 volt. Okay, so from this obtain the voltage regulation. So E0 equal to EPH equal to 275 volt, and therefore percentage voltage regulation is 8.25%. And so in this way we have obtained the voltage regulation of alternator at a lagging power factor. It is plus 26.56. Then for a leading power factor it is minus 25.20%, and for a unity power factor it has been 8.25%. Okay, I hope you understood it. We'll stop here. Thank you very much.